Well, hello, my name is Jose Aguirre, and I'm going to be presenting a paper entitled Physically Based Simulation and Rendering of Urban Thermography. This paper has 5 authors, 3 of them which are from the University of Po in France, which are Elena Garcia, Jairo Acuña, and Benoit Beckers, and 2 which are from Universidad de la República in Uruguay, which is myself and Eduardo Fernandez. So to start off, I'm going to introduce the very basics of radiation. Okay, so everybody that is above the absolute zero emits and absorbs radiation, right? Which is the only heat transfer mode that does not require a medium to propagate. Okay, so this radiation can be characterized by wavelength, right? We have a very wide spectrum of radiation in which only a small part is the visible part of radiation, which is also known as light, right? But there is also a lot of other spectrums or parts of the spectrum, for example, the infrared or the X-rays, which are above or in a shorter wavelength. Okay, so if we go to the real light that reaches the Earth, we can see that the sun can be assimilated as a black body, right? A black body is an ideal kind of body that absorbs all the radiation that gets to it, right? So if we observe the distribution of wavelength in the spectrum that the sun emits, we can see that it's very similar to a black body at the temperature of nearly 6,000 kelvins, right? So we receive this light from the sun, right, in shortwave radiation, or what we call shortwave radiation, which is less than 4 micros, right? And the Earth, because it's at another temperature, right? Of course, it's not 6,000 kelvins, but it's more near to 300 Kelvin, right? The Earth has to re-emit this radiation, right? But because of its own temperature, it re-emits it in long-wave radiation, right? And then, so all the energy that reaches the sun, the Earth from the sun, has to be re-emitted in the form of long-wave radiation, right? There's a difference because short-wave radiation, or typically light, can be seen by our eyes because our eyes have evolved to see the radiation that reaches the Earth from the sun and, of course, passes through the atmosphere. Okay, so we see light. But then the objects here in the Earth also emit radiation, but this radiation is in the form of long-wave radiation, which we are, of course, not able to see. Okay. So this thing is very interesting. It has been a very interesting discovery and has been used for, of course, many things. But one of the things that it has been used is to use urban thermography, or to apply urban thermography. Okay, so urban thermography is basically the art of having a thermal camera, which is a camera that can capture this long-wave radiation and interpret it as colors using, for example, a color map like we see here. Okay, so here we have a picture where we have light, right, the photograph, and then the thermography, or what is also called the infrared image of the same scene. So so the thermal camera captures all the radiation that is reached to it, right? But because the surfaces in the city are not black bodies, but are different type of bodies, more similar to gray bodies if you want, the radiation that reaches the camera is not only the emitted radiation, which of course depends on the temperature of the body, but it's also composed of atmospheric radiations, which is radiation that comes from the air between the camera and the object, and also of reflected radiation, which is radiation that reflects in the object and reaches the camera. Right? So the urban thermography is a really nice tool to understand the thermal exchanges in the city, right, and the thermal or energetic behavior of the city or of the urban surfaces. But it's really hard to interpret thermography, an infrared image, just as it is, right? So in this way, although it provides a specialized view of this distribution of the scene, we have to use other tools to understand it, right? To understand the results of an experimental campaign. Okay, so in this sense, there is the nascent field of urban physics, which has provided like a linkage between environmental and building physics, but also in computing, okay, which is something very needed for this kind of study, where we have the experimental part, but we also need a computational part that allows us to interpret the results. Okay, so this is the area in which we're working and in which we are applying computer graphics techniques to understand the urban behavior. Okay, so yeah, so a little bit of physical basis before going to the full paper itself, right? So we have a concept of emissivity, right, which is defined as the ratio of thermal radiation from a surface to the radiation of a black body. So a black body basically emits, as it absorbs all the radiation, it has to emit all the radiation that it can, right? But if we have a body that is not a black body, then we have something that is called emissivity, which is a value between 0 and 1 that expresses how much of this radiation is actually emitted by the body. But this emission is not always unidirectional or Lambertian, right? We have Kirchhoff's law of thermal radiation that says the emissivity and the absorptivity for a given direction, right, are always equal, dependent, of course, on frequency and temperature, right? Or frequency or wavelength in this case. Okay, so we have what is typically called a gray surface, which is a surface that accomplishes this thing, and it can be said that the radiative flux or the radiative equilibrium at one point of this gray surface depends on the temperature of itself, but also on the temperature of the environment that it is, right? And this is also composed by the emissivity, which will relate these two terms. So one of the motivations behind our paper is the development of a previous work based on a test case in which we went into a street in France, in the city of Bayonne, and performed a thermography campaign, right? We took one picture for each hour for the period of time of 1 day, right? And we captured, with thermal camera, the evolution of temperature of the surfaces in this urban canyon. Okay, and we have some previous results, right, in which we simulated this campaign, the thermography campaign, with a simplified model, and assuming, for example, black body behavior. So we don't have any directional things. We don't have reflections. We only have emission of radiation. So one of the main motivations is taking this example, this test case, and try to compute more detailed results from a computational perspective, using a much more detailed camera and a much more detailed scene, and a much better description of the radiation behavior of the surfaces. So the results for this campaign, we have the set of thermographies, right? The set of thermal images that allows us to see the evolution of temperature throughout a whole day. Right? So as I was saying, the main motivation is using geometries with higher level of detail, right? And analyzes the directional properties of long-wave radiation, right? So we want to see how much is emitted from each point in which direction, right? And of course, using all this stuff, finish and try to simulate and render infrared images. So to simulate these images and to compare the results of our simulations to the actual campaign. Okay. So the proposed methodology here is having an input that is basically the material database, right? The material description of the scene, a 3D model, which is a very detailed 3D model of the scene, as you can see here, which is also useful for doing first, of course, thermal calculations, right? Thermal exchanges, to then get the temperatures and then to do the infrared rendering. So as we see, there is a pre-processing stage where we have to do environmental stuff, like computing the shortwave radiation reaching all the points on the scene throughout the day, also the long wave sky, the exchange with the long wave radiation of the sky, and this allows us to reach the short wave loads and the long wave exchange. Then we have a processing stage in which we don't detail very much in this paper, but it's basically based on the finite element method. So we grab this geometry and all this input and preprocessed radiation data, and we generate the temperature of all the points in the scene, or all the triangles or elements of the scene, to then grab and do the most important part here, which is the post-processing, right? The rendering stage, in which we are going to not be doing shortwave rendering or not be doing light rendering as it's typical in computer graphics, but we're going to be doing long wave rendering, which is different in many senses. Of course, first of all, in the sense of the material definition, because materials behave differently to shortwave than to long wave, right? But also in many other ways. Okay, particularly another important thing is that in shortwave or in light, the light sources are few, and then typically all the rest of the materials or the objects reflect light. Here, all the objects emit light. Right? It's like having multiple light sources or a lot of light sources, and typically area light sources dispersed throughout the scene. Right? So the output here, of course, is the thermograms, or the rendered thermograms. Okay, so for this we propose a particular emissivity model, which is based on the Fresnel curve that we use in computer graphics, but it's also like an interpolation between the Fresnel model and the diffuse model, right? To be able to capture the rugosity or the roughness of the materials. Okay. So we implement several algorithms, but one of the most important, of course, is the rendering algorithm, right? In which we use based on ray tracing, right? Once we have the temperatures of the scene, we use ray tracing to render what is seen by the camera or by the virtual thermal camera, right? And we use, of course, the direct source, but also the reflected source, right? So for this reflected part, we use what is called a microphased BRDF model, right? In which we use GGX, right, based on Walter's paper, right? So we have an algorithm that is basically going to it for each pixel and casting several rays for the reflection using the GGX sampling method, and then computing the temperature directly seen, but also the reflected temperature, and using some radiation mathematics to get the rendered last temperature. Okay. So we're going to be inspecting some results now. Okay, we have this good scene here, right? The scene in here, which is the computed surface temperatures, right? We see the temperatures that are the output of the finite element method, right? We see that the environment or the scene is a really detailed scene, right? Okay, so we have these results for several hours, right, of the same day, of course, with same environmental conditions inputted in the system, and we try to render the image from the same perspective, right, using different directional emissivities, right, using different emissivity models, right. So in this sense, we try the black body, which is basically using no reflections, but we also use a pure diffuse in which the radiation is emitted equally in all directions, right? We also tried the pure Fresnel to show that it's not enough in this test case, that we need to, of course, use different things, because in this case the reflections take a lot of importance, more than it's actually observed in the reality. Okay, and then we finally use the combined model, which is the one that we propose, combining Fresnel and diffuse, right? And we compare this to the actual measured results, right? So as we can see, the combined produces the most similar results, right? There are multiple things that we can see here, but if we compare, for example, the measured with the black body, we can see that there are surfaces that are a lot hotter than in reality, right? Particularly the window blinds down here. right? Pure diffuse also provides better results, right? But we can see that here there are some things that cannot be interpreted or cannot be simulated. For example, we can see that here we have some windows, right? Some windows, glass windows that produce reflection to the sky, which is, of course, the sky is much colder, and that's why we see like this blue or dark blue parts in here that cannot be seen in the pure diffuse. They can be seen in the pure Fresnel, but of course the pure Fresnel has the problem of producing the accurate results in the walls and in the window blinds. So as we can see, if we compare this to our combined results, using of course a variety of materials, but also using different quick curves, like we see in this slide in here, where we see different curves that we can use depending on the material, right? We can see that this kind of combined model can produce very similar results in all of the points in here, right? Considering, of course, this reflected temperature from the sky that, of course, considers the GGX model. Okay. So we can see, if we see more in a more detailed way, we see some spots. We select the final combined result, of course, and we compare the squares, and we can see that we get very similar simulated results. A lot of them which depend on the simulation, of course, but also those who depend on the rendering stage, right? Of course, this can be seen at daylight and, of course, at nighttime also. All right. So to conclude, I have to say that the comparison between thermography and simulated data is a very important and innovative technique, right? It can provide a validation strategy that can be very useful in urban physics, right? Infrared rendering, which is what we have been doing, appears like a very interesting tool to understand the thermal behavior of the scene, particularly comparing the experimental results with the simulation results of infrared rendering can provide a very thorough understanding of the thermal behavior of the scene. We also can say that one of the conclusions is that the current scientific knowledge on the construction materials in the infrared spectrum is very limited, right? So there is a lot to do from the physics perspective to grab a better understanding of this kind of behavior of materials, and of course, particularly of construction materials used in the urban environment. Okay, so and the final conclusion is that all of the code that we used based on MBRI and on ray tracing is available as open source, as an open source package, right? It can be found in this GitHub link. Okay, it's ray tracing based on MBRI kernels to provide of course a faster computational scheme. Okay, so about FeederWorks, there are a couple of things that I'd like to highlight. First of all is using, of course, GPUs to provide a better computational scheme. We think that we have been working lately, but also regarding urban physics, we'd like to study some procedural modeling strategies to actually get the urban meshes that are suitable for finite element methods and then for rendering, right? Which is not an easy task. We had to manually design this detailed geometry that we used. Okay. Another thing would, of course, be studying larger scale scenes, right? Like this one we see here, in these cases, we will, of course, need the integration of fluid dynamics, right? Computational fluid dynamics, which is something that is, of course, much harder, but can provide a much more interesting computational challenge, and of course a much realistic result. It can also provide a significant improvement in the rendering results when compared to the actual experimental campaign. So thank you very much. That was my paper, and I hope you have questions for me today. Bye.